Welcome to a video on families of polynomial functions. A family of functions is a set of functions with the same characteristics. Polynomial functions with graphs that have the same x-intercepts belong to the same family. I actually will do a few examples where it's not necessarily just same x-intercepts, but other characteristics that are shared is also considered a family. A unique equation for a particular member of a family of a polynomial function can be determined if a point on the graph is known, other than the x-intercept, or in other words, you basically need to be given some more information to actually find the unique version of the equation. So let's do some examples. So in this first example, we're told that the degree of polynomial is degree 3. There's a 0 or a root at 4, and another one at -3, and one more at 2. So in terms of looking at the graph, basically we can have the 3 roots that are provided for us, -3, a 2, and a 4. So a polynomial can go through each one like this, a cubic polynomial. I can also do something like this, because we're not told enough information about it. There's quite a few curves that could do this, go through all those 3 points. So as you can see from these pictures, there's many versions of a polynomial equation that would satisfy these given conditions. So a family would be recorded like this, y equals, because we don't know whether the leading coefficient is going to be positive, or like these graphs, green and red, where leading coefficient is negative. I will put an a or some other constant, and then I will have my x plus 3, and then x minus 2, x minus 4 factors because of those zeros. Then I will just have to specify that a, the constant a, could be any real number as long as it is not 0. Because if it was a 0, this would be just y equals 0, which is not a polynomial of degree 3 anymore. Okay? It would be just a horizontal line at y equals 0 instead. If you were given an actual point of the cubic, for example, 3, I don't know, 10, then you could plug this point for x and y into the equation and actually solve for the a and find the unique equation for this family. Let's try another example. So we have degree 4 polynomial, and we have a root of 2. So we can start off by saying x minus 2. The order 1 is multiplicity 1, so it basically has a power of 1, which you don't have to record. Then we have another root at 11 over 2. So x minus 11 over 2. And then this time it says order 2 or multiplicity 2, so we should have 2. Now because it says degree 4, and so far we only have degree 3 written down, because this is x and then x squared, so altogether that's only degree 3. We should have one more factor here with unknown root. So the question here didn't tell us enough information, so we have this t here that could represent another root. Also, we're not told anything about the leading coefficient or the end behavior in here, so I'm going to put a constant a in front. So to finish this off, I will say a could be any real number as long as it's not 0, because if it was 0, like before, it would be y equals 0, which is just a horizontal line, not a degree 4 polynomial. And then this t could be anything except it cannot be the two numbers that we already have written down, because if it was at 2, this would be x minus 2, which could be combined again with this factor. That would make it an order of 2, which is not stated that. It states that it's order 1. And then it can't be that 11 over 2 for the same reason. Another way of writing this factor, actually, so that it doesn't have a fraction, would be to write down 2x minus 11 and then squared x minus d. So this is a better way of recording this polynomial with these conditions. Now, Desmas.com has a cool graphing calculator that I will show visually what we just discussed. So here's my function. I've actually entered A and T that creates the sliders in there that I can manipulate. So right now, what you should notice on the graph is that there is a 0 at 2, and it cuts through that 0 straight line. There's another 0 over here, which is controlled by T. So as I move T around, that 0 changes. And then there's another constant 0 at 5.5, which has a bounce because of the multiplicity of 2. So if I were to shift t to become 5.5, you will notice how the 0 at 5.5 becomes a bend instead of a bounce. And that's what we want to avoid by specifying that t cannot be 5.5 or 2. And the slider A controls the end behavior and the stretch factor of this graph. So as you can see, there's many polynomials that satisfy the given conditions. All right, let's do some more examples. So we have degree 4 again with 2 distinct double roots, and we're only told one of them is at -5. So we'll start out by saying y equals, again, a, because we don't know the end behavior of this. We'll have x plus 5 with a little square. That's what it means for it to be double roots. So we could say order 2, we could say multiplicity 2, we could also say double root. And then we have one more root to create the degree 4 polynomial. So I'm going to say x minus t with a square on that one as well, because it's also a double root. So the conditions for this one would be that a is allowed to be anything except 0, as before, and t is allowed to be anything except the -5. All right. Next example, degree 2, so quadratic with no real roots. This time we're told the y-intercept, so it doesn't have to be only x-intercepts, as I've discussed before. And we're told a particular point. So we want all the families that have no real roots, have a particular y-intercept, and passing through this particular point. So this time I'm not going to use the factored form because we don't know any zeros, and the y-intercept is visible in standard form. So I'm going to start out by saying y equals ax squared plus bx plus c. So standard form or expanded form. We are told that y-intercept is 10. So automatically we know that the c value right here is 10. Then we're told a particular point as well. So point that's given to us is -5 and 10. So you could plug that in for x and y and utilize this information as well to come up with another piece of information. So let's do that. We have 10 equals a -5 squared plus b times -5 plus the 10. So simplifying this a little bit, we will have 10 equal to 25a minus 5b plus 10. So moving the 10 over, we will have 0 equals 25a minus 5b, or 5b is equal to 25a, or b is equal to 5a. So this piece of information, I'm going to highlight in blue, came from the fact that we're given a particular point at -5 and 10. So we still have an unknown value that we don't know. So we know the C. If we knew the A, we would know the B, or vice versa. So we still have one more piece of information that we haven't used, namely the fact that this should have no real roots. So I'm going to do it over here. So no real roots means that the discriminant of the quadratic b squared minus 4ac has to be negative. So I'm going to use this information to continue finding my family. So I will plug in what I know. So b squared is, I'm going to replace it with 5a. So 5a all squared minus 4a, and c is 10. So here we have an inequality with only one unknown a to solve for. So simplifying this, we would have 25a squared minus 40a, oops, 40, for the a less than 0. As you may recall, solving inequalities, you must factor things and then use test intervals to figure out where the answers lie. So I'm going to factor 5a out, and I will have 5a minus 8 less than 0. So the test intervals I'm going to be trying is going to be separated by 0, because 5a is 0 at 0. And then the next one I'm going to separate my interval with, the point is 8 over 5. So 8 over 5, that comes from this other factor here. So I will take a test point less than 0, for example, -1. If I were to plug it into the function that I have here, I would have 5, which is positive, multiplied by a -1, which is negative. And then 5 times -1 would be -5, subtract 8. So negative number subtract 8 would be still a negative. So overall, I have positive times negative. So overall, on this interval, I have something that's positive. Okay. The next interval of numbers, I can try a number, let's say 1. Is it in between 0 and 8 over 5? So trying 1, 5 is positive. So positive times 1, which is positive. And then 5 times 1 is 5 minus 8. That would be 5 minus 8, which is a -3. So we have a negative here. So we have positive times negative. Overall, that would be a negative value in this interval. Notice this testing has to be done with multiplication, because multiplication by positive times negative would be a negative. But if we had addition between this, this would not work. Okay, one final interval to test. Oops, I erased too much. Okay, so the final interval to test is to take a number that's bigger than 8 over 5. So let's say we take 100. So taking 100, we have positive times a, which is 100 we're taking. So it's also positive. And then 5 times 100, and then minus 8 would still be a positive thing. So we have 3 positives multiplied, which result in a positive overall. Okay, so we want to solve this inequality when it's less than 0, meaning the output should be negative. So here we have our outputs. We have positive outputs on this interval, negative outputs here, and positives here. So we're interested actually in numbers in between 0 and 8 over 5, but not including those. So final answer is the following. We would have the family ax squared plus, instead of b, I'm going to write down 5ax plus 10, comma, a is a number in an interval from 0 to 8 over 5. Once more, I'm going to use Desmos.com graphing calculator to prove to you that my answer is correct. So here we have our family entered with a constant a, which is controlled by the slider. Right now, the slider is set to be lower than 0, not like our condition is specified. So if you look at the graph, we have a condition of y-intercept being 10, which is true. We have a condition of -5 and 10 being the point, which is true as well. But this function right now has real roots right here and here. So if I were to move the slider so it's between 0 and 1.6, 1.6 being 8 over 5, notice how now we have no real roots, but the other two conditions are still there. And if I went even further down, closer to 1.6, you can see how this parabola gets closer to the x-axis. At 1.6, it's going to have exactly one root, which we do not want to have. All right. In our next example, we're told that we have degree 3. At least one root of the 3 real roots is at 4, meaning that we have 3 real roots, and one of the roots we're told is 4. We're given the y-intercept, and we're given a point. So because we are given a root, I'm going to start off kind of like a mix of factored form and standard form. I'm going to start off by saying that we have x minus 4 as a factor. And then the other part will come from a quadratic. We need degree 3, so this is linear, times quadratic would be the degree 3 cubic. So ax squared plus bx plus c is the remaining part of this polynomial. So I'm going to go through and start with maybe the y-intercept information. I'm going to plug in a point. I'm going to record this point as 0, 8. I will plug this point in and eliminate one of these unknowns. We have a, b, c that are unknown. We want to eliminate as much as possible using the information provided. So 8 is equal to 0 minus 4, a times 0 squared plus b times 0 plus c. So working this out, you'll have 8 is equal to negative 4c, or negative 2 is c. So this is a piece of information that came from the information I highlighted in yellow. The next thing I will do is use my other point. So here we have 0.16 that again I will plug in. So let's plug this in. So 6 is equal to 1 minus 4, a times 1 squared plus b times 1. And I'm going to record my c as negative 2 already. And simplifying this, I'll have 6 is equal to negative 3, a plus b minus 2. I'm going to divide both sides by negative 3. So I have negative 2 is equal to a plus b minus 2. And moving the 2 over, I will have 0 is equal to a plus b. Or in other words, that a has to be negative b. So this condition came from the one that I'm going to highlight in blue. So it came from the 0.16. So let's see what we still have not used. So we've used the y-intercept, we used the point. We haven't used the fact that there will be more zeros. We're told there's 3 real roots. So I'm going to highlight that in green. So what does that mean for us? Well, this quadratic here, it means that we have some more roots from this quadratic. And we know that if a discriminant of a quadratic is bigger than 0, there are 2 real roots. So let's start off by saying b squared minus 4ac has to be bigger than 0. So once more, we have an inequality to solve. I'm going to plug in b squared, I'll leave as it is, minus 4. Instead of a, I'm going to use negative b, as was specified in this quantity over here in blue. And then my c value was negative 2, bigger than 0. Simplifying, we would have b squared minus 8b greater than 0. Factoring b out, we'll have b bracket b minus 8 greater than 0. And once again, solving this inequality, we're going to use test intervals. The intervals are going to be split up at numbers 0, because that's the factor b that creates the 0. And the factor b minus 8 creates number 8. So our intervals are split off from negative infinity to 0, or from 0 to 8, or 8 to positive infinity. So let's start with less than 0. So taking a number less than 0, like negative 1, using that in this factor and then in this factor. So in this factor, that would be a negative, and negative 1 subtract 8 would also be a negative. So overall, negative times negative is a positive. Next interval, we can use a number like 2 in between 0 and 8. So using a number like 2, this would be positive. And then 2 minus 8 would be a negative number. So we have a positive times a negative, which is overall a negative in this interval. And lastly, we would have a positive here, just because something positive multiplied with something positive would be positive. So final answer, because we want this inequality to be bigger than 0, but not equal to 0, our interval that we should be taking is something lower than 0, but not equal to 0, and anything bigger than 8, not equal to 8. So to state final statement of the family would be to write down the equation y equals x minus 4. And then because this is all about the b's, I'm going to rewrite this all in terms of b's. So a is negative b, so negative b x squared plus bx minus 2, comma, b is specified to be in the interval from negative infinity to 0 or from 8 to positive infinity. You can verify this answer using a graphing calculator yourself. We'll do one more example. So here we have degree 3, and we are given 2 roots of the 3 roots possibly, and the y-intercept, and we want to record it in standard form. So we're actually not told whether this will have 3 roots or just these 2 roots. We're not told multiplicity at all as well. So we'll take that into consideration when we're solving this. So because we're given roots, I'm going to start with factored form. So we're going to have x plus 1. We're going to have x minus 2 as a factor. I'm not specifying multiplicity because we're not told that. And then we're going to have one more factor. This factor has to be a linear factor. So you have a choice. You can create an a out here and then do x minus t as we've done before. Or you could do something like this. You can have x plus 1, x minus 2, and then the linear factor ax plus b. So it kind of follows what we did with quadratics above. So this linear factor is has a and b that we don't know, but we are told one more piece of information that we haven't used yet. The y-intercept is negative 2. We have used the other information here. So I'm going to start off by plugging in a point, and the point that I'm going to use is point 0, negative 2. And plugging that in, you would have 0 plus 1 in the bracket, 0 minus 2, and then a times 0 plus b. This simplifies to negative 2 equals, it would be negative 2b. So b is 1. You could have also went with the first version. So I'm going to do that in red just as a comparison. So plugging point negative 2, 0, or 0, negative 2 in. So using red color, I'm going to have negative 2 is equal to a 0 plus 1, 0 minus 2, and 0 minus t. So this simplifies to negative 2 is equal to positive 2t times a. So in this situation, because we still have 2 letters, we can maybe solve for the t. So we'd have negative 1 over a is our t value. And then if you put that back inside, you'll notice that you'll have actually the same thing as we have in the previous question. We'll have y equal to a, x plus 1, x minus 2, and then x plus 1 over a. And if you were to put this a inside of this last bracket only, you would have x plus 1, x minus 2, and ax plus 1, which is exactly what we would have if we followed with this version here. B is 1, so 1 here would be ax plus 1, or ax plus 1 as we have here. So we're practically done. We just need to specify that a is allowed to be any real number, and it just cannot be 0, because if it's 0, we would have basically multiplying by 0 out in front, the whole thing becomes just a constant 0, not a degree 3 polynomial. I'm not going to say that a cannot be negative 1 or positive 2 because we're not told that these roots could be non-repeating. So I'll leave it just like that. The only other specification is that we have to record it in standard form. So let's FOIL this out. We would have x squared minus x minus 2, and then ax plus 1 And expanding a little bit more, we would have ax3 plus x squared minus ax squared minus x minus 2ax minus 2. And then collecting like terms, we would have ax3 plus 1 minus a with an x squared. So think of this as basically common factoring x squared out. I'm just writing it behind the common factor. Is usually written in front. This time I'm writing it behind so that this is a coefficient. And then plus -1 minus 2a in front of x minus 2. So a is allowed to be anything except 0 so that the conditions provided are satisfied. I hope this was helpful to you.